Good. Okay. Good afternoon, everyone, and thank you very much for joining today's instalment of the Energy Futures Lab Lunchtime Seminar Series. My name is Sandy. I recently graduated from Sustainable Energy Futures MSc at Imperial, and I'm now a consultant within energy transition, which seems to be quite a common pathway for people from that course. Today I'm here to present the findings of my thesis completed here at Imperial, titled Exploitation of UK Industrial Demand to Reduce the Cost of Green Hydrogen Produced via Offshore Wind Energy. In terms of context, I'll spend roughly 25 to 30 minutes going through introduction, methodology, focusing on the research findings and discussion, and concluding the results of my thesis, leaving plenty of time for a Q&A and also so you guys can get a bit of a lunch break. But as we go along, also there's space for time for Q&A then, but if there's anything that's completely unclear, please just shout as we go along. So as we're all aware, it's critical to limit the average global increase in global temperatures to 1.5 degrees C above pre-industrial levels. The UK aligns with global ambitions, committing to net zero emissions by 2050, part of the Climate Change Act 2008, as I'm sure you all know. And industry is a key focus area for these decarbonisation efforts. There has been a lot of progress since 2000 towards 2020 and up until today. However, these efforts are not sufficient to reach decarbonisation targets set out in the UK's industrial strategy for decarbonisation. At present, industry is the third highest emitting sector in the UK, accounting for 14% of nationwide emissions, or 63 megatons of carbon dioxide equivalent in absolute terms. So essentially, industry, as it may seem by these numbers, it is a necessary evil. It's vital to creating the products for modern life, and moreover, the decarbonisation technologies for other sectors, such as solar panels or other renewable energy facilities or energy efficient building materials. So it simultaneously facilitates and complicates the net zero transition, requiring innovation of clean energy technologies via targeted and rapid policy intervention. Hydrogen, as I'm sure you've all heard of, offers an alternative fuel and feedstock for the industrial end user. However, at the moment, modern hydrogen production is undeniably reliant on fossil fuels, primarily created via steam methane reforming, or SMR, to create what is known as grey hydrogen, which is very polluting, referred to as heavy carbon. However, hydrogen can be created via low carbon means, such as steam methane reforming with carbon capture, utilisation and storage, or renewable energy powered electrolysis, referred to blue and green hydrogen respectively. The government expects demand to grow exponentially for hydrogen to 460 terawatt hours by 2050, addressing 20 to 35% of national energy consumption. This includes replacing current hydrogen consumption as well as new applications across the board. To reach this massive energy consumption, the UK government plans 10 gigawatts of production installed capacity by 2030, and this is going to be a twin track of green and blue hydrogen. So at least 5 gigawatts of this 10 will be green hydrogen, subject to economic affordability and viability. However, traction still remains very, very slow for green hydrogen. Ultimately, green hydrogen has been demonstrated technologically, but experiences no demand pool given a weak business case for adoption, assigned a technology readiness level of 6. Hence, it has not been commercialised. Sidestepping from hydrogen to another big topic in the renewable energy landscape of the UK. The nation is a world leader in offshore wind, aiming to nearly triple its capacity by 2030 to 50 gigawatts, and on a route to 65 to 125 gigawatts by 2050. However, curtailment is a common issue in the UK, by which wind farms regularly power down to address issues related to limitations on the grid or unfavourable wind speeds, which ultimately wastes zero carbon energy, although the purpose is to balance supply and demand. Curtailment across 2020 and 2021 for offshore wind offered sufficient energy to power 800,000 homes, costing the government £299 million in 2020 and £806 million in 2021 under the pay-as-bid mechanism, by which no matter what the offshore wind producer creates, the government has to pay for it. no matter whether it's curtailed or actually used. And the projected increase in offshore wind's cumulative installed capacity, in line with UK's national targets, is expected to trigger greater levels of curtailment. And this is where it links into hydrogen, because this creates an opportunity to leverage otherwise wasted renewable energy for the production of green hydrogen via curtailed offshore wind-powered electrolysis. So despite the twin-track approach that I discussed earlier on, proposed by the UK government, green hydrogen is the strategic option. Production using offshore wind energy, namely curtailed energy, is particularly compelling, capable of bridging the disconnect between the hard-to-abate industrial sector and the nation's growing renewable energy capacity. The figure on screen presents a simplified flow of curtailed offshore wind energy moving to electrolysis to produce green hydrogen delivered to the industrial end user, which forms the basis of my thesis. Very simplified basis, but the basis nonetheless. The challenge is that green hydrogen uptake faces several barriers to adoption, chiefly the cost. It is much more expensive than green and blue hydrogen, let alone traditional fossil fuels. So my thesis sought to assess the hypothesis that the use of curtailed offshore wind energy and the exploitation of industrial demand in the UK, incentivised by policy intervention, may be sufficient to narrow the cost disparity between green hydrogen and its alternatives, sustain economic competitiveness, and stimulate widespread adoption of hydrogen fuel and feedstock throughout the UK and further afield. First, the research evaluated whether the supply of green hydrogen produced via curtailed offshore wind is sufficient to address the demand from 2025 through 2050, or if additional dedicated offshore wind resources are required to address the deficit. Second, the research developed a novel, see if I get this right, a novel optimization-based multi-period mixed integer nonlinear programming representation of a market penetration assessment to evaluate impact on the total cost of green hydrogen to the industrial end user under the individual influence of policies and as an aggregate policy mix. The research employed a multi-layer methodology illustrated on screen. The study first established the supply of green hydrogen required to satisfy demand between 2025 and 2050, assessing whether that produced via curtailed offshore wind energy is sufficient or if dedicated resources are required to address the deficit. Comparing the flow of green hydrogen to blue and grey on a monetary basis established a baseline cost disparity to be addressed by policy intervention. Therefore, subsequent modelling of energy policy fed the overall objective of establishing economic competitiveness, assessing the impact of policy on green hydrogen cost from the perspective of the industrial end user. And that's the final part here on the bottom right, which is the market penetration assessment, completed in Excel using Lindo's What's Best optimization tool. So lots of equations on screen, but we'll keep it high level for the first part of the methodology, which is the energy flow balance, to think, we've got all this curtailed offshore wind, is it actually enough to address demand going forwards? Equation 1 calculates the annual supply of curtailed green hydrogen compared to industrial demand on an energy basis via equation 2. So essentially, if alpha I is less than 1, that means curtailed offshore wind produced green hydrogen is not sufficient to meet demand, and then we require supplementary resources. Equation 4 to 7 then calculate the energy flow cost of green, blue and grey hydrogen respectively to establish the cost disparity between green hydrogen and its alternatives and evaluate the cost reduction required to establish cost competitiveness, which is the overall aim. The thesis considered 3 policy interventions individually and in aggregate as part of the modelling process. First, the Industrial Hydrogen Accelerator Programme, or IHAP, which is capital funding of 26 million for innovation products promoting fuel switching to hydrogen, and that would be deployed between 2020 and 2030. That's the plan. The Emissions Trading Scheme, or ETS, I'm sure a lot of you are aware of the emission trading scheme, but essentially it places a tax on production processes within the UK dependent on what their carbon intensity is. So if you're more carbon intensive, you're going to be taxed more. And finally, the low carbon hydrogen production business model, or HBM, which provides revenue support to hydrogen producers to address the elevated costs relative to natural gas. So it kind of works very similar to CFD. If a hydrogen producer says it costs me X amount, but natural gas is this much cheaper, the government will pay a premium to say, here we go, this establishes cost competitiveness for you, and we've addressed that cost disparity that obviously costs the government a lot of money. The overall aim of the thesis translates an objective function in the model of minimising the total cost of green hydrogen to the industrial end user across the period of 2025 through 2050, shown at the bottom on screen, which calculates the cost of green hydrogen for the end user, less the financial repercussions introduced by, say, the IHAP, the ETS, or the HBM. And that then gives you a final answer saying this is what we're trying to minimize across the period, such that you can reduce that barrier to entry and allow to stimulate the adoption of green hydrogen in industry. The model sets the industrial demand per year as a variable, allowing the value to fluctuate between a maximum and minimum bounds, driving the assessment of whether industrial demand can be exploited to realize a cost reduction. For moving on to research results, are there any questions on the methodologies from the room? Okay, at the moment, cool. So the analysis considered 3 scenarios: an optimistic, midline, and pessimistic scenario based on the data input to the model to address uncertainty with the values. So, for example, as I said earlier, offshore wind could be between 65 and 125 gigawatts in 2050. So that gives us a range. Offshore wind load factors may change. That gives us a range. Electrolyzer efficiency may change. That gives us a range. And that allows us to establish 3 different scenarios to give a range of results and then assess, the likelihood of this actually going ahead. The predicted supply of curtailed green hydrogen is inefficient for the growth in demand. Insufficient for the growth in demand expected from 2025 through 2050, which can be shown on screen by, you can see that it drops straight away from 2025 down below 100%. So that tells us that creating green hydrogen via curtailed offshore wind power alone is not enough. We need to also have dedicated offshore wind facilities. Therefore, the answer to the first research question is quite simply no. Supply green hydrogen, specifically that produced via curtailed offshore wind energy, is insufficient for industrial demand from 2025 through 2050, requiring dedicated generation facilities to address deficit. Nonetheless, an opportunity exists to realise a green hydrogen cost reduction by utilising curtailed electricity, even when complemented by dedicated offshore wind facilities. Leveraging curtailed electricity achieves a total cost reduction for the industrial end user of 8.8 to 18.7%. The reason being is that this energy is otherwise wasted. It's free energy that can be used. So if we leverage it, it's free. It's going to reduce the levelized cost of hydrogen. And that can be shown on screen. It can be quite a difficult graph at first to understand, but essentially what it's saying is that these are all the costs of alternatives relative to hydrogen produced via dedicated offshore wind in conjunction with curtailed electricity. So you can see the negative value compared to dedicated green hydrogen tells us that using curtailed electricity realizes a cost reduction. However, even once we've done this, it's a step in the right direction, but the cost relative to blue and grey hydrogen is still greater. So blue hydrogen and grey hydrogen are still cheaper. Therefore, still require policy intervention to address this cost difference and establish cost competitiveness for green hydrogen moving forwards. The model considered each policy individually and then in aggregate. I won't go through every single scenario because we'd be here for hours. So I'm going to highlight some of the key findings. Consider first the IHAP alone. Quite simply, the grant creates negligible impact, although well intended. Think about it, this grant is £26 million, and it's great the government's announced that, but looking at the cost disparities that we've seen, those are in the order of billions of pounds. So £26 million from between 2020 and 2030 is hardly going to make a dent. So that got rid of it from the research. It wasn't going to do anything. But then consider a combination of the hydrogen business model and the emissions trading scheme in conjunction. The emissions trading scheme imposes a tax on the production of hydrogen proportional to carbon intensity. Therefore, blue and grey hydrogen are taxed higher than green hydrogen, with a view of disincentivizing heavy carbon production. Conversely, the hydrogen business model offers support to hydrogen producers adhering to low carbon hydrogen standards, so it's less than 20 kilograms of carbon dioxide emitted per kilogram of hydrogen, in the form of a government paid premium, thus reducing the levelised cost of hydrogen and the price of green hydrogen to the industrial end user. Individually, the policy measures expect cost parity of green hydrogen, but combining the policy measures realises cost competition in the least time of any of the scenarios considered in the thesis, which is shown on screen. The policy mix establishes a strong business case for green hydrogen in the short term and sustains a cost reduction through 2050 to take advantage of economies of scale and learning by doing and stimulate cross-sector adoption. So again, that can be shown on screen, that you can see we've got blue hydrogen and a blue hydrogen policy relative to green hydrogen. That tells us that by introducing the policy, you can see that it's automatically reducing and going below. That tells us that green hydrogen is cheaper from 2025 onwards. However, conversely, if we don't put in policy, it remains above zero, and that's telling us that green hydrogen remains too expensive to implement within industry. So do we have a solution? It seems quite simple. Put in the ETS and hydrogen business model, and that's a go. Critically, the issue is that the current approach to raise the funds required for the hydrogen business model, which offers a premium, is a new hydrogen levy, which is expected to trigger a £118 increase per annum for household and business energy bills if the levy is placed on domestic and commercial gas bills in accordance with the government's policy for rebalancing costs. The Treasury quite simply seeks to avoid the expense of kickstarting a domestic hydrogen economy, given the financial environment that we're in right now, quite understandably. However, placing an additional green levy on end users is not a fair option, especially given most domestic households and businesses will not benefit from a new supply of hydrogen. Applying a flat rate across energy users, regardless of financial means, is not the correct route, risking a decline in support for hydrogen amongst the public, as well as the wider net zero agenda. However, there is an option that was explored in the thesis, and that is establishing a closed-loop budget, essentially leveraging the revenue generated by the emissions trading scheme for the government for the premium paid for low carbon hydrogen production in the HBM. So that's the closed loop. Take the money from the ETS generated for government and put it straight back into the hydrogen business model, rather than having to introduce a new hydrogen levy. The figure on screen illustrates the extent to which the annual revenue generated by the ETS can drive the HBM, achieving 21 to 23% across the pessimistic, midline and optimistic scenarios across the period considered. And the whole point of this is to typify the fair and strategic approach required for all net zero objectives. It can't just be we put it in and put the money on the public. You have to have some system in place to actually make it an economically viable business case. So let's recap. The UK industrial sector is undeniably reliant on fossil fuel energy, thus generating copious amounts of greenhouse gas emissions and impeding the transition to a clean energy future. However, industry is a necessary evil. We need it for modern life, as well as creating new clean energy technologies for other industries, simultaneously facilitating and complicating the net zero transition and requiring targeted policy intervention. Hydrogen, specifically green hydrogen produced via curtailed offshore wind energy, offers an attractive solution to bridging the gap between the hard-to-abate industrial sector and a growing renewable energy capacity. Nonetheless, green hydrogen faces several barriers to industrial adoption, chiefly the cost. The research assessed the hypothesis that the use of curtailed offshore wind energy and the exploitation of industrial demand in the UK, incentivised by policy intervention, is sufficient to narrow the cost disparity between green hydrogen and its alternatives, namely blue and grey hydrogen. The thesis deems the supply of curtailed green hydrogen inadequate for the projected increase in industrial demand above the 2025 baseline, but nonetheless demonstrates that curtailed electricity offers an opportunity to realise a cost reduction towards establishing cost competitiveness for green hydrogen with grey and blue. The IHAP capital funding, as I said, useless, let's get rid of that, but looking at the emissions trading scheme and the hydrogen business model, it is a brilliant way and it can establish cost competitiveness for green hydrogen from 2025 onwards. And that's brilliant. It's a great recommendation. However, to build on that critically is that there's an opportunity to partly fund the HBM via the ETS in a closed loop budget to typify the fair and strategic approach required for achieving net zero targets. Additionally, just to finish it off, as I said at the start, green hydrogen is currently in a twin track approach with blue hydrogen. But I think what the thesis has demonstrated as well is that green hydrogen is a strategic approach, both in terms of its less emitting than blue, and also is subject to all these brilliant policies such as the IHAP, HPM, and ETS that can stimulate widespread adoption from 2025 onwards, setting us on a route towards net zero for the industrial sector, whilst satisfying industrial demand, maintaining economic competitiveness, and not pushing businesses abroad. So that is everything from me today. I know it's been quite a whirlwind of information, but I would like to leave plenty of time for questions. So if there's anything, I can go back in the slides, discuss whatever you want to talk about. So please let me know. Yeah.
The ETS income that you're talking about here, is this new ETS income, or is this existing ETS income that could be rediverted?
From 2025 onwards, so just understand the question, you're talking about ETS income that's already in the budget, or?
Yeah, exactly.
Not including that, so all focused on just looking at ETS income from hydrogen production from 2025 onwards, and then rerouting that round. It would be quite interesting to also take into account the potential of, for example, free allowances that would create even more income towards the HBM, or, for example, a cross-border adjustment mechanism similar to the EU.
But those monies are non-existing and not planned for currently under the UK.
No, they're not. So ETS doesn't have any projections of how much it's going to make, or it's just allocated to general spending budget. So it doesn't have any particular use. So that was then made the thought process that if it has no particular use, let's make sure that it's still used within the net zero agenda and put towards the hydrogen business model, which at the moment has no budget, no idea how they're going to fund it, other than potentially a new hydrogen levy. Yeah.
So is this kind of contingent on the producers agreeing to make green hydrogen? But what's your kind of opinion on like energy storage is kind of development? They might sort of see that as an avenue to kind of avoid curtailment as well. So do you think the production of green hydrogen is a better kind of use of their energy for them?
Yeah, so you're purely from the hydrogen producers' point of view. It was the reason that industry was chosen, probably should caveat to this, is that industry is the largest consumption source in the UK of hydrogen. So if all the hydrogen producers, they could put it into storage, and then if you, via capacity market or whatever, you could get the electricity, sell it when the prices are high if you store it overnight. But that would be a business case for the hydrogen producers to create and see, where they're going to get the most money. But my focus is more on how can you get green hydrogen lower, because ultimately we're always going to need hydrogen. I know there are all these new applications that kind of overlap with energy storage, but the root application of hydrogen is as a feedstock in chemicals or ammonia, and that's always going to be needed. So you're always going to need hydrogen no matter what. But yes, the new applications kind of overlap with the energy storage, and that's the case for the offshore wind producers to think, what's the best route for them. But I'd recommend green hydrogen just because I like it. Cool. Yeah.
But pink hydrogen, I know, the hydrogen thing. How does that play in? Have you considered that, or is it not really?
At the moment, I think if you were looking at a market such as France, where I think France is 70% nuclear energy, that would be a lot more viable. That'd be really interesting to look at. But I started with the UK, purely the whole thought process first started with that figure of £806 million wasted for curtailed electricity. And that's what then stemmed, how can we use that? Where can we put it? Green hydrogen industry. So it's that thought process. Pink hydrogen in the UK, I think it's a bit more interesting. I think the nuclear base is, if we could barely get enough electricity from offshore wind to create the hydrogen produced. So I doubt that we're going to have enough electricity from nuclear in the UK, but France would definitely be an interesting study. Thank you. Yeah.
Thank you for the amazing presentation, but I was wondering, like, since I have seen some prediction before for like, if we are having a bigger economic of scale for the hydrogen production, it would bring down a lot the cost of hydrogen production. So from your prediction that there's an expensive premium for using the hydrogen, which is the main part of the cost that make it like lose the advantage comparing to other type of hydrogen.
So just clarify your question, it's what's the main cost driver for green hydrogen, or
what is the main kind of like main cost that increase the price for the hydrogen production
of green hydrogen relative to it's purely comes down to the likes of economies of scale and learning by doing. So if we take green and blue, blue and grey, where grey it currently accounts for like 95% of the production of green hydrogen. Cheaper. However, with new technologies coming in for electrolysis, that's where the issue comes. Electrolyzer capacity is still on the rise, and it still requires a lot of supply push from research and development to make them cheaper and more affordable. Also requires a demand, needs a demand pool to realize economies of scale and learning by doing. So it's not necessarily that the technology is any more difficult to understand or any more complex. It's just that the demand's not there, so it's more expensive. Does that make sense?
So for your like opinions, do you think that at the point of 2050, will they have enough economics of scale to make the price come down a bit, or does you take it into consideration?
Yes, well, that's kind of according to the modeling. If we had the likes, because you're only going to realize economies of scale and speed that up if you introduce policy to reduce the barrier to investment. That means people then come in, they start producing green hydrogen, they start using electrolyzers. That then stimulates the economies of scale and learning by doing. So policy is the first step. And then, as I showed earlier on, this one, under the HBM and the ETS, you can realize cost competition for green hydrogen. And then if you start adopting that, because it's the low cost option compared to blue and grey from 2025 onwards, that's going to reach economies of scale by learning by doing. And according to my analysis, by 2050, yes, it will definitely be sufficient to then remove the policy interventions, because those economies of scale and learning by doing have taken effect. Yeah. Cool. Yep.
What is the difference in emissions between blue hydrogen and green hydrogen? Because my understanding of it was, well, it's wrong, I'm sure, but it's that blue hydrogen is meant to not have any emissions, but does it just in the extraction of the fossil fuels and stuff like that?
Yeah, so it's carbon capture and storage. It's a brilliant technology. However, current commercial rates for the capture is about 70%. So it's still a massive chunk of it that's released to atmosphere. If you want to bring blue hydrogen down to, I think blue hydrogen is currently around 5 kilograms of CO2 per kilogram of hydrogen, whereas green can be near zero, less than 1, 2. If you wanted to bring carbon capture, blue hydrogen down to the same level as green, you'd need a carbon capture rate of around 98, 99%. And whether that is technologically or financially viable is a huge question. Hence why there's a lot of thoughts around blue hydrogen as an interim solution, but long-term switching to green. That's most likely why the government have announced a twin track. But in future, my opinion is that it will shift more to green hydrogen, especially with the growing renewable energy capacity. Yep.
So as I understand it, the current UK strategy for getting green hydrogen going with offshore wind farms is to kind of get it into clusters.
Yeah.
So offshore wind farms next to the factory, so it's all closer together,
yeah,
and therefore more feasible. In your opinion, how does that strategy go with your projections? Is that the correct track in your opinion?
It's a bit out of scope of my work, but yes, I definitely understand. There's a massive cost in terms of, if you're creating offshore wind that is way offshore, and then do you put the electrolyzers with the offshore wind turbine, do you send the electricity to shore, then create the hydrogen? That's all related to efficiencies, what's going to be the most cost optimal. So that's why it's moved towards your point of the strategy of clustering it and putting it together. Within this work, it was the techno-economics where, I based the techno-economic inputs off a range of literature, and that ranged for, cases where the hydrogen was produced 10 kilometers offshore to produced onshore in clusters. So it was taken into account, but I think if you were to cluster it, it would actually make it more cost efficient, and this could be even more aggressive.
Did you take into account temporal factors in your production of green hydrogen?
It did in terms of projections of 2025 through 2050 for the likes of mainly technological things, so offshore wind, load factors, installed capacity, electrolyzer efficiencies, and those all came from techno-economic projections, which took into account learning rates and economies of scale. But that's then what gave me, because obviously it's not exact, you might have a range, so that's what gave the pessimistic, optimistic, and midline scenario.
I was thinking more about the variability of the curtailment periods.
Yeah.
Because obviously that will only happen at various points in the year when it's probably sunny and windy at the same time, for example. So, but from a production perspective, that means that you're only producing when you've got excess energy. You're only producing in short bursts at various points.
Exactly.
I mean, your plant to be fairly inefficient, I think.
Yes, exactly. I think brilliant to keep going with that research. It wasn't available, and I did think about it in terms of, when is the electricity going to be available, but that granularity of data isn't available. And I think if it was going to go into that, it would potentially require a pilot plant study or more advanced modelling to go ahead. But then that's potential that just use the curtailed electricity to generate hydrogen and then send the actual electricity straight to the grid, just so you're not wasting it. My hypothesis was that we had to address all demand with curtailed electricity. That's not necessarily the case. You could just address a little bit of it just to send it off so it's not wasted, acting similarly to the previous question as more of an energy storage rather than the pure source of green hydrogen. Thank you very much, everyone.